Hello and welcome to everyone watching this video. Today we are going to talk about tensor cores and why they are considered the powerhouse of deep learning acceleration. So, what are tensor cores? Well, for those who haven't heard of tensor cores, these are dedicated specialized hardware accelerator cores designed specifically for matrix multiplication and convolution operations. And unlike traditional CUDA cores available in your NVIDIA GPUs, tensor cores are optimized for their specific mathematical tasks, which form the backbone of deep learning algorithms. And unlike the general purpose CUDA cores, which most of us are already familiar with, tensor cores are a very specialized set of cores capable of performing 4x4 matrix multiplications in just a single go. Over here in this GIF, you can clearly see the performance of CUDA cores in the leftmost image, and the other three images represent tensor cores for varying precisions. Next, we move on to SEXP. Well, SEXP stands for single precision AX plus Y operations. Now, if we look carefully, each of these 4x4 matrix to matrix multiplication operations is a complex operation consisting of 64 simple scalar multiplication operations. To perform such complex operations, it would require 64 CUDA cores executing the operations in parallel. Thus, with the tensor cores, we can already observe a significant boost in the performance. However, given these cores are so specialized at the job they do, it may not always be useful, as there are certain requirements that need to be met. For example, the dimension of the matrices need to be a multiple of 8, or the data type should be supporting. Otherwise, the operations would automatically fall back onto the CUDA cores. These fallbacks actually happen quite often. Thus, we don't generally see a direct 8x or even a 16x boost in performance as officially claimed by NVIDIA. Practically, it is not feasible to observe the performance using tensor cores alone, that is a different thing, as they always need CUDA cores alongside to fall back on. Now, let's talk about the supporting data types. Tensor cores allow half precision, which is FP16, and automatic mixed precision, or AMP, as the two supported floating point precisions. Automatic mixed precision, or AMP, means that we pass inputs in half precision, that is FP16 over here. The tensor cores perform the multiplication and store the intermediate results in FP32 or full precision, and then these results are accumulated together and stored in FP32 itself, and then those results are then passed on back to the user as an output. This means the input data loading time to the memory has now reduced because of the half precision inputs, but we still get to see outputs in higher precision. Now let's consider an example. And well, I have used the following paper to generate this example. This is a paper of my own, and the title is Evaluating Multi Instance DNN Inferencing on Multiple Accelerators of an Edge Device. This paper was submitted and got accepted at IEEE International Conference on High Performance Computing, Data and Analytics. Well, talking about the example, for this example, we have used ResNet 50 model. The framework over here is PyTorch. There are various accelerators that have been used for this paper, which are FP16, FP32, and AMP. And we have varied the batch sizes, which means that the each batch passed on to the ResNet model contains different batch sizes varying from 1 till 64, and we run two instances of the ResNet 50 model concurrently. Now there is this one note that needs to be considered. The paper also talks about few other accelerators like DLA and also CPUs apart from uh, Tensor cores and CUDA cores. But because that is not something that we are discussing over in this video, we will be skipping over them. So now let's consider the results from this example. If we look in the graph, we have got results for all of them, for CPU, for CUDA cores, CUDA plus Tensor, CUDA plus DLA, and also CUDA plus Tensor plus DLA. However, for the purpose of this video, we would only be focusing on CUDA and CUDA plus Tensor results. So as we can see that there are varying batch sizes that we have considered, varying from batch size 1 till 64, all of them encoded in different colors, both for CUDA as well as for CUDA plus Tensor. Now from the numbers that we can see over here on the y-axis for throughput, we can see that there is a significant jump, that is between 40 to 50% of a performance increase when we go from CUDA cores alone to CUDA plus Tensor cores. This is something interesting to see, given that the model accuracy hasn't really changed a lot. In fact, it actually remains pretty much the same, around 76%. And while maintaining the model accuracy, we are still able to observe some significant boost in the performance. So, are there any further references which you could refer to? Sure, there are a bundle of resources which online available which you could be using. However, there are certain useful articles and videos which I have listed down over here, and I will also make sure that I add the links to all of these resources in the video description down below as well. So do make sure to check them out. And with that getting said, I thank you all for watching this video, and let's hope to see you in the next one.